Imagine for a second that you are behind the wheel of a high-performance electric vehicle. You're just completely flooring the accelerator, surging up this really steep, winding mountain road.
Oh, yeah.
And inside the cabin, it is serene. I mean, it feels incredibly smooth. It's almost completely silent. But underneath you, like deep inside the motor casing, there is this invisible, violent war against physics happening right at that very moment.
Right, the contrast there is just staggering between the peace of the cabin and the extreme thermal and, well, electrical stress happening in the powertrain. We expect that silent, smooth power delivery, but we rarely think about the multi-layered engineering safety nets functioning in, literal milliseconds to keep everything from melting down.
Yeah, melting down is not an exaggeration.
No, not at all.
So what does this all mean? Today, we are executing a comprehensive deep dive into the exact technical specifications of these motor overtemperature diagnostics and safety strategies. We're going to trace the entire life cycle of motor heat, from the root physical causes of a meltdown to the hardware and software defense systems, the design and manufacturing preventative measures, and finally, the grueling validation tests these systems just have to survive before hitting the road.
It is a fascinating journey because we rarely experience catastrophic motor failure in the real world, and that isn't by accident. It's entirely because of these overlapping layers of protection. So to really appreciate how those nets are woven together, we have to start with the basic physical reality of, why an EV motor gets dangerously hot in the first place.
Right. Before we can talk about the defense systems, we need to understand the anatomy of a meltdown, or like the fault root cause analysis, as the source puts it. And it all begins with this concept called Joule heating. Now, I've seen the formulas in the notes, but let's break this down into plain English. What is actually generating this heat when I floor the accelerator up that mountain?
Think about the stator, which is the stationary part of the motor packed with coils of copper wire. When you're in an extreme dynamic scenario, like full throttle acceleration or demanding massive torque to climb that mountain, the motor requires huge amounts of electrical current, right?
Okay.
These massive phase currents have to flow through those stator windings to create the magnetic fields that turn the wheels. Now, copper is an excellent conductor, but it isn't perfect.
Right, it still has some resistance.
Exactly. It has physical stator resistance. When you push massive amounts of current through that resistance, it creates friction at the atomic level. And that friction manifests as heat. This is Joule heating or I²R heating.
And the trick here is the scale of it, right? Because the heat doesn't just increase a little bit as you push the pedal harder, it scales exponentially.
Precisely. The formula for Joule heating relies on the current squared. So if your motor demands twice as much current to get up a steep hill, it doesn't generate twice as much heat, it generates 4 times as much heat.
Wow.
Now, under normal circumstances, the car's thermal management system handles this perfectly. Liquid coolant circulates and just pulls that heat away.
But the nightmare scenario happens if that cooling system degrades in some way. Let's say a coolant pump starts to fail, or a microscopic blockage forms in a pipe, or there's a slow leak.
Right.
Suddenly you're generating exponential heat, and it just has nowhere to go.
The heat gets trapped. The stator core and those copper windings rapidly reach what engineers call thermal saturation. We are talking about internal temperatures skyrocketing to 130 degrees Celsius, and in extreme cases, hitting 150 degrees Celsius.
Which is well over 300 degrees Fahrenheit.
Yep.
And this is where the sources highlight something I found incredibly revealing. When the temperature spikes that high, the heat doesn't just threaten to melt things. It actually changes the physical properties of the motor in real time. This is called parameter drift.
What's fascinating here is how this isn't just a heat issue, right? It's a multi-physics coupling problem. The physical reality of the motor warps. So the physical stator resistance, the property that determines how electricity flows through it, that spikes by 30 to 40%. In extreme heat saturation, that resistance can actually double.
Oh, wow. So it literally becomes twice as hard to push the electricity through.
Exactly. And furthermore, the permanent magnets inside the motor, which are essential for generating torque, they begin to lose their magnetic flux. The heat literally weakens their magnetic field.
So to put that into perspective for the listener, imagine you're driving a car down the highway and you go to take a curve. But mid-turn, your steering wheel suddenly changes its physical sensitivity by 40%.
Right.
The car's brain, which is you, the driver, is calculating your turn based on a normal steering wheel. But the physical reality of the wheel has completely warped in your hands. You would oversteer or understeer and you'd crash.
That is a fantastic analogy because in the world of EV motor control, we call that crash a model mismatch. And to understand why this is so dangerous, we have to look at how modern electric vehicles figure out when to push and pull their internal magnets. Many use sensorless control algorithms at high speeds.
Okay, let's pause there for a second. Sensorless control algorithm sounds like a bit of a contradiction. How does the car control the motor without sensing what it's doing?
It's a bit of a misnomer, yeah. It just means it's not relying on a physical mechanical position sensor, like a resolver at that moment. Instead, it calculates the exact position of the spinning rotor by reading something called back EMF, or back electromotive force. Essentially, as the motor spins, it acts a bit like a generator, pushing a small amount of electricity back into the system. The software uses complex integration math to read that back EMF, calculate the rotor's exact angle, and fire the electrical currents at precisely the right millisecond to keep the motor spinning smoothly.
Ah, I see. So it's using the electrical feedback itself as a kind of virtual sensor.
Yes.
But here's the catch. If the physical resistance of the copper wire has doubled because of the heat and the magnets have weakened, the math equation the computer is using to read that back EMF is now fundamentally broken.
Yes, exactly. The math is expecting a cold motor, but the physical motor is boiling. So this back EMF integration generates massive additive errors in the software. The control vectors become completely misaligned with the actual physical position of the spinning rotor. The magnetic fields stop pushing and pulling in sync, so the motor becomes mathematically blind and it simply stalls out.
And a stall at high speeds is dangerous enough. But the source material outlines this fatal domino effect if the car's computer tries to save itself the wrong way. So if the motor control system detects a severe issue, it might trigger a safety protocol called an active short circuit, or ASC.
Right. And ASC is normally a brilliant safety feature. If you lose control of the motor, the inverter intentionally shorts all the electrical phases together. This stops the motor from generating dangerous, uncontrolled high voltages while it spins down. It acts like an electrical brake.
But wait, if short-circuiting the motor is what causes massive, fatal heat spikes, why would they intentionally short-circuit to save it?
It's a matter of choosing the lesser of two evils.
Okay.
If you let a malfunctioning motor freewheel at high speed, the back EMF voltage can spike so high it instantly blows up the entire battery pack and the high voltage systems. An intentional short circuit safely clamps that voltage down to zero. The trade-off is that you dump all the spinning kinetic energy of the car into the motor as pure heat.
And that brings us to the nightmare. If ASC is triggered when the motor is already sitting at 150 degrees Celsius, it generates massive symmetrical short-circuit currents, peaking at around 3,390 amps. You are dumping a massive surge of thermal energy into a system that is already boiling.
Right. And combining 1,390 amps of short-circuit current with 150-degree ambient temperatures pushes the permanent magnets past their point of no return. You risk irreversible demagnetization.
Wow.
Once a permanent magnet gets too hot, its atomic structure scrambles, it loses its magnetism forever. If you demagnetize those magnets, the motor is permanently destroyed. It's no longer an engine, it's just a very heavy metal paperweight in the back of your car.
Not to mention the pure physical degradation going on at the same time. I mean, long-term exposure to those temperatures, combined with the high-frequency physical vibrations of the motor spinning at 10 or 12,000 RPM, literally cooks the enamel insulation painted onto the copper wire.
It does.
The lacquer breaks down, it cracks, and suddenly you have raw copper touching raw copper. The current jumps straight to the ground, causing a catastrophic short circuit.
And it gets worse. High heat also rapidly ages the rubber O-rings and seals separating the mechanical gearbox from the electrical motor. If a seal fails, you get oil, water, or gases leaking right into the motor cavity. That creates conductive pathways for electricity to travel where it shouldn't, completely destroying the electrical integrity of the system.
Okay, so we have established the absolute worst-case scenario. The heat warps the physical reality of the motor, blinds the software, and physically melts the hardware. So how does the car's computer fight back before that happens? Let's dive into the digital immune system, the technical architecture, and the software-hardware co-diagnostics.
To prevent that entire chain of events, engineers utilize an ASIL D architecture. ASIL D is the absolute highest classification of safety hazard defined in the automotive industry. It dictates that you cannot just rely on one sensor or one line of code to save the car. You need multi-layered, overlapping hardware and software diagnostics working in a cross-lockstep formation.
Let's start with the hardware layer, the first line of defense. Deep inside the motor stator, buried right in the copper windings, engineers embed NTC thermistors.
Right.
These are tiny, highly sensitive temperature sensors. Their sole job is to convert the physical heat into an analog voltage signal ranging between zero point 0.5 volts and 4.5 volts. That signal is sent straight to the main microcontroller unit, specifically the AURX TC3XXV ADC module.
And the crucial detail here is the rigid enforcement of that voltage window. The hardware enforces what is called out-of-range detection. Under normal functioning circumstances, that sensor's voltage output must stay strictly between zero point 0.5 volts and 4.5 volts.
Why that specific window? I mean,
Yeah.
why not just 0 to 5 volts?
Because 0 volts means the wire is cut. 5 volts means it's shorted directly to the power supply.
Oh, I see.
By establishing a baseline of 4.5 to 4.5, the hardware comparator can instantly identify a physical break. If the voltage drops to 0.2, the system doesn't need software to think about it. It's a hardwired microsecond-level reflex. It instantly flags that the sensor wire is broken, shorted, or has lost power. Furthermore, that main microcontroller, the brain of the operation, has internal dual sensors monitoring its own physical temperature, ensuring the computer itself doesn't suffer thermal runaway while trying to save the motor.
So the hardware acts like a physical tripwire. It's incredibly fast. But what about the software? Because checking for a broken wire is one thing, but how does the code actively monitor the creeping thread of heat?
This is where we get into some really elegant engineering mathematics. The software runs a continuous background model called the MRAS, the Model Reference Adaptive System. It doesn't just passively read the temperature sensor, it dynamically estimates the physical resistance of the entire motor in real time based on a mathematical formula.
I saw this exact equation in the source material, and without reading it like a textbook, if I'm understanding it right, they are basically using the fact that copper's electrical resistance changes predictably with heat to use the entire stator wire as a giant secondary thermometer.
You've nailed the concept perfectly. Copper behaves incredibly predictably. Its electrical resistance increases by a very specific coefficient positive 0.393% for every degree Celsius it heats up above room temperature.
Right.
Because the software knows exactly how much voltage it is applying to the motor and exactly how much current is flowing back, it can calculate what the electrical resistance is at any given millisecond. By tracking how that resistance changes, it can mathematically deduce exactly how hot the copper must be.
But wait, I have a big question about this setup. If that tiny NTC thermistor, the physical temperature sensor we talked about earlier, is physically sitting inside a boiling hot motor, bouncing around under intense vibration, couldn't the sensor itself just get damaged or cooked and start lying to the computer? I mean, could it send a signal saying the motor is a safe 80 degrees when it's actually melting at 140 degrees?
That is exactly the vulnerability that the ASIL D architecture is designed to catch, because the system uses what we call a doer-checker lockstep model. The software MRAS calculation acts like a real-time polygraph test for the physical hardware sensor.
A polygraph test. How does that play out?
Well, the software is constantly looking at the physical impedance, the resistance calculated from the actual electricity flowing into the motor. It takes that real-world mathematical reality and constantly compares it to the story the physical NTC sensor is telling. If the copper math says the resistance is characteristic of 140 degrees, but the little sensor is sitting there claiming it's only 80 degrees, the system immediately knows the sensor is either lagging, insulated, or failing. It catches the lie, flags the mismatch, and triggers the safety protocol instantly.
Wow. It trusts the sensor, but it ruthlessly verifies it with the math. And if it confirms there is a dangerous heat issue, it triggers the safety fallback.
Exactly. And the fallback response is scaled to the severity of the threat. If it's just mild heat, say you are pushing the car a bit too hard up a hill on a hot day, but it's not critical yet, the system initiates a limp home thermal derating.
I was reading about this derating slope. It smoothly cuts the maximum output torque by 500 newton meters per second, bringing it down to within 30% of its rated value. What does that actually feel like to the person behind the wheel?
You would suddenly feel the car lose a significant amount of punch. The acceleration would become sluggish. It might feel annoying in the moment, but the car is intentionally throttling itself to stop the heat generation while still allowing you to safely merge off the highway or limp home to a mechanic. You still have control, you just don't have power.
But if it is severe heat, if the system detects total thermal desaturation or critical parameter drift, it doesn't mess around with limp mode.
No, it triggers a much more aggressive response. It executes a stepwise active short circuit or a mixed voltage modulation or MVM, and
Wow.
it has to execute this shutdown within the fault-tolerant time interval, which the sources note is incredibly strict, less than or equal to 60 milliseconds.
Wow.
It forces the system into a safe state before that catastrophic model mismatch we discussed earlier can permanently destroy the hardware.
Okay, let's unpack this. We have this incredible digital diagnostic system that can catch physical faults in microseconds and lock down the motor in 60 milliseconds. But, as engineers always say, a problem avoided is infinitely better than a problem solved on the fly. How do they design the physical motor from the blueprint stage to just not fail in the first place? That gets us into part 3, the DFMEA key design prevention controls.
Right. When you are drafting the blueprint, in the design failure mode and effects analysis phase, or DFMEA, you have to design the physical architecture to resist these thermal pathways from the start. That begins with thermal co-design. The engineers design custom integrated heat sinks specifically for the heavy-duty power components.
Just to clarify, when the sources mention silicon carbide or IGBT components, these are basically the massive heavy-duty electrical switches inside the inverter that turn the battery's direct current into the alternating current the motor needs, right?
Exactly. They handle immense amounts of power, so they generate immense heat. The engineers obsessively minimize the thermal resistance anywhere these components, or the motor stator itself, make contact with the cooling jackets. They want the heat to have the widest, fastest escape route possible into the liquid coolant.
But even with great cooling design, extreme heat can still happen if you drive the car hard enough. And we talked earlier about that terrifying model mismatch problem, where the software goes mathematically blind because the stator resistance doubles and the readings warp. The source material outlines an incredibly clever hardware solution to this software problem called the search coils patent.
This is truly an elegant engineering solution. The engineers realized that if the main stator windings are vulnerable to resistance spikes and magnetic saturation at 150 degrees, they simply shouldn't rely on them for critical rotor position data during a thermal crisis.
It's just too risky.
It's too risky, so they redesigned the wiring harness of the tiny NTC sensor itself into what they call search coils.
So they essentially turned the temperature sensor's wiring into a backup antenna.
Essentially, yes. These search coils are wound into the motor, but they are physically and magnetically decoupled from the main three-phase windings that actually drive the motor.
Oh, I see.
Because they aren't carrying the massive driving currents, they are completely immune to the resistance drops, the inverter dead zones, or the deep magnetic saturation that is wreaking havoc on the main power coils.
So even if the main motor is experiencing massive diameter drift and the software math is falling apart, these little decoupled search coils are just sitting there, completely unaffected, providing pristine, redundant ANDL estimation to the computer. It completely solves the blindness issue.
It acts as an anchor to reality when the rest of the math goes haywire. But the DFMEA goes further, particularly regarding how they manage that active short circuit, or ASC, that we mentioned earlier. Remember we said that intentionally shorting the motor dumps massive heat into the inverter's power switches to save the motor.
Right. And if the entire system is already approaching 130 degrees Celsius, triggering a massive short circuit could just melt the inverter instead, creating one meltdown for another.
Exactly.
So the engineers implemented what the sources call an alternating upper-lower arm ASC strategy.
Yes. The inverter that controls the power has upper and lower power bridges. Instead of just shorting one side and forcing it to take all of the thermal punishment until it melts, the software state machine dynamically takes turns. It shorts the upper power tubes for a moment, letting them absorb the heat, and then switches and shorts the lower power tubes.
Okay, let's unpack this with an analogy. Imagine you're carrying a massive, heavy bag of groceries home from the store. If you just carry it in your left arm the whole way, your left bicep is going to give out. The muscle will fail, and you'll drop the bag.
Right.
But if you carry it in your left arm until it gets hot and tired, and then smoothly switch the bag to your right arm and just keep alternating back and forth, you distribute the physical load. You can make it all the way home without dropping the bag. By passing the extreme thermal load back and forth between the upper and lower bridge arms, they keep any single component from hitting its absolute melting point.
It is a brilliant active thermal state management strategy. It buys the entire system the critical seconds it needs to safely dissipate the spinning kinetic energy of the motor without permanently cooking the hardware. It directly addresses that model mismatch vulnerability we talked about.
It is brilliant, but here's a reality check. You can have the most brilliant blueprint in the world. You can have search coils and alternating ASC strategies designed perfectly in a computer simulation. But a perfect blueprint doesn't survive sloppy hands. If the assembly on the factory floor isn't perfect, the math falls apart.
Which is why we have to transition to the production floor, the process failure mode and effects analysis, or PFMEA. How does precision manufacturing physically lock in these safety designs?
The first thing that jumped out at me in the manufacturing notes is their approach to poka-yoke, which is the Japanese term for mistake-proofing a process so a human literally cannot mess it up. When it comes to installing those critical NTC temperature sensors on the stator, manual human installation is strictly banned. It is completely forbidden.
You absolutely cannot trust human hands for this step. If a human operator presses the sensor in, they might use slightly unequal pressure or leave a microscopic air gap between the sensor and the copper winding. In thermodynamics, an air gap is a powerful insulator that creates contact thermal resistance, meaning the heat from the motor won't transfer instantly to the sensor.
So the sensor would lag, the copper could be boiling, but the sensor is sitting comfortably behind a tiny pocket of air, telling the computer everything is fine, completely ruining the polygraph test we talked about earlier.
Precisely. So, to physically prevent this, they use industrial robots performing 3D trajectory potting. The robots inject a specialized high thermal conductivity fluorosilicone glue perfectly around the sensor in a three-dimensional pattern. And the factory doesn't even trust the robots entirely.
Really?
Yeah, they follow the injection immediately with 100% automated optical inspection, or AOI. High-speed cameras map every single sensor to guarantee there are absolutely zero microscopic voids or missing glue. Only then does it move down the line.
It's incredible. And it's not just the sensors. We talked earlier about how extreme heat and vibration physically cook and crack the enamel insulation on the copper wire, leading to short circuits. To prevent that, the factory floor uses a process called VPI, vacuum pressure impregnation.
VPI is one of the most critical steps in the entire build. They place the completely wound copper stator into a massive vacuum chamber. First, they pull a deep vacuum to suck out every single molecule of air from between the thousands of tightly packed copper wires.
Okay.
Then they pump in a liquid insulating resin under high pressure to fill all that negative space. The factory strictly locks down the pressure curves and the baking temperature curves used to cure the resin. But more importantly, they use online viscosity monitoring of the liquid resin itself before it's even injected.
Why do they care so much about the thickness or viscosity of the resin?
Because the margins for error are microscopic. If the resin is too thick, it won't penetrate deeply into the center of the wire bundles, even under high pressure. If it's too thin, it might run out of the bottom of the stator before the heat bakes it solid. Either way, you risk leaving microvoids, microscopic bubbles of nothing inside the insulation. Under the intense stress of 150-degree heat and high voltages, those microvoids become the exact physical weak points where electrical voltage breakdown occurs. A spark jumps the gap through the bubble and your motor instantly shorts out. The viscosity monitoring ensures the physical integrity of the insulation is absolutely flawless.
Which brings us to the wire connections themselves. Because an EV motor isn't just a contained box of copper wire, it has to connect to the inverter, the battery, and the rest of the car. And here, the engineers are fighting a stealthy phenomenon called fretting.
Fretting is a severe issue in any high-vibration, high-temperature environment. It's essentially microscopic motion. As you drive, two metal electrical connectors vibrate against each other at high frequencies. This microscopic rubbing constantly scrapes off the invisible protective oxide layer on the metal, exposing fresh raw metal to the air, which then instantly oxidizes again. Over thousands of miles, this builds up a thick, crusty layer of oxidation, which acts as a powerful electrical resistor.
And tying it all back to the beginning, increased electrical resistance means increased Joule heating. More heat causes more rapid oxidation, which causes more resistance, which causes more heat.
If we connect this to the bigger picture, hardware degradation is almost never linear. It is exponential. A tiny bit of oxidation from a rattling wire increases resistance slightly. That increases the heat slightly, which accelerates the fretting and oxidation. Suddenly, you are in a runaway thermal event that melts the connector, simply because a pin vibrated a fraction of a millimeter.
So to stop this exponential decay at step 0, before it even begins, the manufacturing process implements two massive controls. First, the wire crimping heights and compression ratios are mathematically locked to create what they call a cold weld. They compress the metal pieces together so densely that they essentially fuse. There's physically no room for micromotion.
Right.
Second, they use an automated machine to inject a space-age grease right into the connector pins.
Yes. Niogel 760G.
I had to look this up because it sounds like sci-fi. It's a specialized fluorosilicone conductive grease that actually contains a chemical copper passivator.
Yeah.
The machine injects it, and this continuous oil film totally encapsulates the entire contact surface. It physically blocks oxygen and atmospheric moisture from ever reaching the metal, preventing the fretting oxidation cycle from even starting. I mean, they banned human hands and use space-age passivating grease just to make sure a tiny electrical pin doesn't rust. It's wild.
It is the ultimate expression of mistake proofing. You eliminate the failure mode at the molecular level on the assembly line. But of course, you can't just assume your robots, your vacuum chambers, your grease, and your math equations are perfect. Eventually, you have to prove it.
Which brings us to the final phase, the torture chamber. The Design Verification Plan and Report, or BVP&R. Before a single motor is approved for mass production, they take this beautifully engineered, perfectly manufactured unit, and they do their absolute best to destroy it.
They subject it to trials that deliberately simulate the absolute worst-case real-world scenarios, multiplying the thermal, electrical, and mechanical stresses simultaneously. The goal isn't just to see if it runs, it's to force the safety math to prove it holds up in reality.
The first trial is based on the ISO 16750D3 automotive standard. They take the full motor assembly and bolt it to a 6-degree of freedom shaker table. This is a massive machine that violently vibrates the motor across all spatial axes at varying frequencies, from 10 to 2000 hertz, with greater than 35 meters per second squared of acceleration.
It's essentially simulating driving a heavily loaded vehicle over the worst rutted washboard dirt road imaginable at top speed continuously. But they don't just shake it in a warehouse. They put the entire vibrating shaker table inside a sealed environmental chamber.
Of course they do.
While it's violently shaking, they cycle the ambient temperature from a freezing negative 40 degrees Celsius all the way up to a boiling positive 150 degrees Celsius. And they leave it in this torture chamber for over 300 hours.
300 straight hours of freezing, boiling, and violent shaking. To pass the test, the acceptance criteria are incredibly strict. Even after all of that abuse, when they pump high-voltage direct current through it, the insulation resistance, which proves the VPI resin held up, must remain massive, greater than or equal to 100 megohms at 500 volts DC, meaning no microvoids cracked open.
Right.
The contact resistance at those grease pins can barely change, proving the cold weld and the Niogel prevented fretting. And the NTC thermistor readings must remain perfectly stable, proving the robotic potting glue didn't let an air gap form.
It comprehensively proves that the physical manufacturing processes can survive a lifetime of abuse. But proving the physical hardware is only half the battle. They also have to prove that the software's digital immune system can actually catch the swinging trapeze when things go wrong.
Right, which leads to the Bino test, the algorithmic takeover in extreme heat. They bolt the motor to a dynamometer, which measures power output, and they intentionally push it so hard against so much resistance that the internal stator cooks to over 130 degrees Celsius. They deliberately push it into that thermal saturation danger zone we talked about at the very beginning.
So at this exact moment in the test, the physical stator resistance has doubled. The magnetic flux has weakened. The motor is deep into dangerous parameter drift.
And then, while the motor is screaming at high RPMs under this massive thermal load, the engineers intentionally sever the physical resolver signal. They physically cut the main hardware wire that tells the motor where the rotor is.
And instantly, the software is mathematically blind in the middle of a high-speed, high-heat run.
Here's where it gets really interesting.
Yeah.
To pass the test and prevent a catastrophic stall, the software must seamlessly detect the missing signal, abandon its primary math, and switch over to that MRAS background model and those decoupled surge coils we discussed. And it has to execute this entire diagnostic and handover in under 5 milliseconds.
Yeah.
I just love the mental image of this. It is the algorithmic equivalent of a high-wire acrobat performing a routine, suddenly having a blindfold slapped over their eyes in midair, and having to instantly catch the swinging trapeze using only echolocation. They have a 5-millisecond window to catch the bar. If they miss, the motor stalls out, current spikes, and it destroys itself.
But if they pass, the system catches it perfectly. The acceptance criteria demand that during this 5-millisecond blindfolded handover, the torque output can barely waver, torque ripple has to be less than or equal to 5 Newton meters, and the electrical angle estimation error must stay strictly under 5 degrees. There can be 0 stall faults and 0 overcurrent faults. The motor just keeps running as if nothing happened.
It proves that the catastrophic model mismatch is solvable in real time. But there is one final test, the most brutal of all, the ASIL demagnetization test.
They spin the motor up to a blistering 12,000 RPM under full load, completely saturated with heat, and then they intentionally pull the trigger. They initiate the active short circuit. They force the motor to dump all of its kinetic energy into itself.
They force the short-circuit currents to spike, simulating that fatal domino effect. To pass, the software's ultimating ASD strategy, our grocery bag analogy, must successfully pass the thermal load back and forth between the power bridges fast enough to survive. The bus voltage has to clamp safely at less than or equal to 720 volts, and the massive short-circuit current must be mathematically capped at under 550 amps.
And the true test happens after the motor finally stops spinning. They don't just look at a green check mark on a computer screen. They take wrenches and physically tear the motor down to its base components.
Wow.
They extract the permanent magnets and test their magnetic field strength. The strict acceptance criteria demand a 100% zero irreversible demagnetization and absolutely no physical burning or melting of any internal components.
This teardown is the ultimate reality check. The sources point out that engineers can use advanced Python tools to calculate complex formulas, like the ASC demagnetization decoupling armature time constant, to perfectly simulate how the short-circuit current should decay on a computer screen. But a computer simulation doesn't drive you up a mountain. Physical validation is the only thing that proves the math actually translates to physical reality. It proves the permanent magnets survived the massive electrical spike entirely because the alternating thermal strategy actually worked.
It is a monumental validation process. When you trace the entire journey from the sheer atomic physics of Joule heating, through the cross-lockstep algorithmic polygraphs, down to the robotic assembly lines and the vacuum impregnation chambers, all culminating in 300-hour torture tests, it is an incredible amount of overlapping engineering dedicated solely to managing heat up to 150 degrees Celsius.
And it forces you to realize how much invisible, highly coordinated effort is happening every single second you are on the road. We expect the car to just work, but we are completely blind to the multi-layered war being fought and won under the floorboards in less than 5 milliseconds.
And looking at all this complexity raises a crucial question for the future of the industry. The source outlines this incredibly robust architecture designed for today's motors, which saturate around 150 degrees. But the EV industry is pushing relentlessly for even smaller, lighter, solid-state motors with massive torque requirements. As motors get physically smaller but more powerful, the power densities are going to skyrocket.
Oh, absolutely. I mean, they want the power of a semi-truck and the physical footprint of a shoebox.
Precisely. And if it takes this much computational power, decoupled search coils, and specialized aerospace grease just to keep a motor from melting at 150 degrees, how will our software and materials need to evolve when future hyperdense motors routinely hit 200 degrees Celsius or more? At a certain thermal threshold, standard copper and magnets simply break down. Will our software algorithms eventually hit a hard mathematical limit where no amount of Duratyk logic can save the motor, forcing us to invent entirely new physical metamaterials just to prevent meltdowns?
That is a staggering thought. The math and the software can only compensate for so much before the physical reality of the metal simply gives up. It's definitely something to think about.
Yeah.
So the next time you were driving your EV and you decide to floor it up a steep hill, enjoying that perfectly smooth, silent ride, just remember the incredible symphony of engineering working in the background to keep the physics in check. Thanks for joining us on this deep dive.